All right, when it comes to oxidation states and using this table here, we've got some interesting things. So first of all, let's look at this table. So when we have the ion, the monatomic ion, we're just going to have oxidation states as the charge of the ion. So like sodium here would have a charge of +1. Chloride would have a charge of -1. So when we have an ionic compound, which remember ionic compounds, those are things that are metals bonding with non-metals. So whether it's a transition metal or just, an alkali metal or an alkaline metal, those things, when we have them bond with non-metals, the things over on the right side of the periodic table, they will create ionic bonds, okay? So in those situations, those single atom ions just have the charge of the ion. Everything else, basically, if it's in its elemental form, like solid sodium up here, you can see solid sodium, gas, oxygen gas there, or ozone gas there, or even liquid mercury. Those things in their elemental state and beyond these examples, so it could be something like solid zinc, or it could be something like solid potassium, right? Those things have an oxidation state of 0. Everything else we basically look at from these things right here. Fluorine has a charge of -1, oxygen has a charge of -2, generally speaking, and hydrogen has a charge of +1. And then we'll predict what the other compounds' charges would be based off of that information right there, okay? So when we're looking at an example, like in 15, we've got solid sodium mixing with chlorine gas goes to sodium chloride. The first thing we have to do is look for the oxidation states of these things individually. So sodium here is in its elemental state. So it, wow, I'm struggling. Sodium is in its elemental state, so it has an oxidation state of 0. So is chlorine. So even though chlorine is not an example up there in that chart, it still is in its diatomic elemental state as a gas, so it has a charge of 0. Then they combine and create sodium chloride, which is an ionic compound, okay? And that means that whatever the ion charge is, that will be the oxidation state. So sodium has an oxidation state of +1, or an ionic charge of +1, so its oxidation state is +1, and chloride has -1, okay? So now what we have to look at is we need to see, okay, which of these substances then was reduced and which was oxidized. And when we're looking at oxidation versus reduction, remember we use the mnemonic Leo says grr. That means losing electrons is oxidation, gaining electrons is reduction. So there's a little bit of complication here because electrons are negative, so when you're gaining electrons, you're becoming more negative, which is kind of backwards of how we normally think about that. But that's just what we have to think in terms of the electrons, right? So when we're looking at the gain or loss of electrons, I see sodium, its charge changed, or its oxidation state rather, changed from 0 to 1, +1. That means that it has actually lost an electron because it became more positive. So if it loses an electron, it actually is oxidized, okay? So sodium here has lost an electron, so sodium is oxidized, okay? And I'm also speaking sodium, the atoms, not necessarily the solid, okay? Now I look at chlorine, and chlorine has become more negative, which means it has gained an electron. And when we have an electron that is gained, that has been reduced. So chlorine is reduced. Now, when we're looking at oxidizing and reducing agents, those are basically the opposites, right? So sodium, because it lost an electron, it is actually, it has reduced, it is the reducing agent, okay? So sodium, the solid, now is the reducing agent. And chlorine, the gas, and now see how we're in the whole compound, that is the oxidizing agent because it received that electron. Okay, so those are the three things. The first thing is right here that we're asked to do. Second thing is right here. And this is the third thing in each of those problems. So now let's look at a compound that is not ionic, okay, because we looked up here and sodium chloride is an ionic compound because it is a metal mixed with a nonmetal. But down here we have C3H8 and oxygen, right? And those are not ionic. So C3H8 is not ionic, so we're going to have to look back up at these rules. I have to analyze, okay, carbon, does it have a rule? Hydrogen, does it have a rule? What is going on here? So I look back up here, and I see that hydrogen has that +1 charge. So hydrogen is going to have, each individual atom will have a +1 oxidation state, not charge, sorry, oxidation state. And there are 8 of them. So that's a total of +8 for the oxidation state. Okay, because carbon does not have a rule, I actually have to work from this back up to carbon's oxidation state. So carbon needs to have a total of -8 for its oxidation state because this is an electrically neutral compound, so I have to have those charges cancel out, those oxidation states cancel out. And because I have 3 carbon atoms, that means each carbon atom is going to have a -8/3 oxidation state, okay? So I just separate these electrons or these charges directly to each atom by just dividing them out, okay? So it can be a fraction. I know it's a little goofy, but it is possible. So the oxidation state of each carbon atom is -8/3. Now oxygen here on this right side, or on the right side of the reactant still, it is in O2, which is its elemental state. You can see up there. So its elemental state has a charge or oxidation state of 0. All right. So now we need to look at the oxidation states on the right side. And again, these are not ionic compounds. They're all nonmetals with nonmetals. They're covalent, which means we have to look at our rules. So I'm going to look at first, again, I see that carbon is up here, but I know that carbon doesn't have an oxidation rule, but oxygen does. Oxygen, each oxygen atom has a -2 oxidation state, and I have 2 of those oxygen atoms. So that means oxygen has a total oxidation state of -4, even though each individual atom is -2, and that's really what we're looking for there. That's why I write this within these parentheses, to show I'm acknowledging each oxygen atom has an oxidation state of -2, and I have 2 of those oxygen atoms to make a total oxidation state of -4. And the reason I need to do that is I need to, again, use this to discover carbon's oxidation state. Because there's no electric charge on this molecule, they have to be equal and opposite charges. So carbon needs to have a total oxidation state of +4. And because there's only one carbon atom, that carbon atom will have an oxidation state of +4. Okay. Then let's tackle hydrogen, water. Okay, anyway, let's tackle water. H2O and hydrogen has a +1 oxidation state, and oxygen has a -2. So those are both things on my actual chart there. So there we go. Those even out. So now we've got all of our oxidation states set. Now we have to analyze which things lost electrons and which things gained electrons. What changed its oxidation state, okay? So I see on this left side, each carbon atom has a -8/3 charge, and on the right side, the carbon atoms have a +4 charge. So that's a pretty big swing of electrons there. The other thing I look at is hydrogen. Okay, so hydrogen has a +1 charge, and on the right side, the product side, it also has a +1 charge. So it has not changed at all. So we don't have to worry about that. That's not going to be anything we're looking at. But what we are looking at also is oxygen. It had an oxidation state of 0 on the reactant side, but on the product side, everywhere it has a charge of -2. Okay, so that means it has also changed. So the things I'm analyzing here are going to be the carbon atoms in C3H8 and the oxygen atoms, okay? So the carbon changed, and it went from being very negative to being more positive, okay? So if it is becoming more positive, that means it's losing electrons. And again, Leo says, grr, if it loses electrons, Okay, if it becomes more positive because those negative charges are leaving, it is oxidation. So carbon here is oxidized. All right, and then if you gain electrons, which means you're becoming more negative like oxygen did, right? We gained electrons, so we gained negative charges. That means oxygen was reduced. Okay, so we've got our oxidized compound and our reduced compound. And now we're going to look at, okay, what about the things that were oxidizing them, the oxidizing agent and the reducing agent? So when carbon was oxidized, it was oxidized by the oxygen gas. So oxygen is the oxidizing agent. And when oxygen was reduced, our C3H8 was the reducing agent. Okay, it was the thing that was accepting those, it would also be appropriate to say that carbon was the reducing agent. Okay, so hopefully that gives you a little bit clearer of a picture on oxidation reduction reactions.